Hello, my name is Dr. Gopolang Mohlabeng. I am from South Africa. South Africa is a country at the southernmost tip of the continent of Africa, over here. And as you can see, it's far away from Canada. It's about a 17-hour flight between Canada and South Africa. So I'm a theoretical astroparticle physicist at Queen's University, and I am a postdoctoral research associate at Queen's. So today's topic I'm going to be talking about is called dark matter. When we look up at the night sky on a very dark night, if we're lucky enough to get away from the city, away from the light pollution in the city, we see a beautiful picture. You could see the Milky Way picture. We see stars in much more higher definition than we would in the city. So see a picture almost like this. And if you have a telescope, even a small one, you may be able to see galaxies, planets, even more structure like these ones. And I should say that there are billions and billions and billions of these. And in fact, when we look up at the sky, we can see that there are billions of stars. Right? So we ask ourselves, is this all our universe is made of? At least this is what I asked myself when I first saw these. It turns out that all that stuff that we can see, all these billions and billions of gas, galaxy clusters, galaxies, stars, actually only make up about 5% of our universe. About 27% is in an unknown form of material we call dark matter. The only thing that we know about dark matter is that it exists. And then about 70% of our universe is made up of an even more unknown entity we call dark energy. And we know almost nothing about it. And so I spend most of my time trying to really excited about it and trying to answer this question: what is dark matter, and how do we go about finding it? So one of the biggest evidences we have that dark matter exists is in how galaxies rotate. So when if we look at a galaxy face on, Newton's laws tell us that this is the left is supposed to be the picture of the galaxy. Basically, the stars that are closer to the center should be orbiting the center of the galaxy much faster than stars further away from the center of the galaxy. Remember, in our solar system, Mercury rotates around, which is the closest planet to the sun, rotates around our sun much faster than the Earth, which is further away from the sun, and much faster than Neptune, which is much further away from the sun. So we expect this from Newton's law. However, what we see is that actually the galaxy rotates almost the same. At the scale of a galaxy, the rotation of stars closer to the center and those that are out towards the edge actually is almost the same. So where Newton's laws tell us that this is what we should be expecting with the velocity, that the velocities of stars should be falling off as we move further away from the center, what we observe is actually different, that the velocities further away as we move away from the center become almost constant. This tells us that there is some mass that we can't see, that is unaccounted for, that is surrounding our galaxy and causes this peculiar kind of behavior in our galaxies. And so this is one big evidence, and we see this in many, many galaxies that we observe. And this is one big evidence that we have that dark matter exists at the scales of our galaxy. And why is dark matter important? Well, dark matter is important because it shapes the universe as we see it today. It forms galaxy clusters, it forms galaxies. Galaxies form solar systems, like also in our case, we have the solar system. The solar system has the Earth, and the Earth has life. So without dark matter, we wouldn't actually exist today. And how dark matter forms galaxies is by trapping visible matter into gravitational potential well, that then ends up forming the structure called a galaxy. One way to kind of visualize this is to make an experiment, and we can do this at home, is to take a rubber sheet and stretch it out. and take a bowling ball, a heavy bowling ball, and put it in the center of that rubber sheet, you'll see that it causes a dip in that rubber sheet. Take marbles or ping pong ball or something smaller than the bowling ball and just throw it on the rubber sheet. And you'll see that it gravitates towards that dip that has been caused by the bowling ball. Now let's for a second close our eyes and imagine that the rubber sheet and the bowling ball are invisible. Now we see all these marbles and smaller materials that are clumped up in the center and just being suspended in air and not gravitating around anything, right? And so this is actually how, because dark matter is invisible to us and forms these gravitational wells, it traps these structures. It traps materials to form these structures, and we see them as galaxies and galaxy clusters. And so my job as a theoretical astroparticle physicist is to come up with models of what dark matter could be and how we go about finding. And that's it. Thank you.